Okay. You're off then, Nick. See you later. Okay, so you've all just done 2 weeks of the first wind tunnel experiment. Okay, that's all over and done with. You're now going to go straight into different experiments using the same equipment. It's the boundary layer experiment. Boundary layers are another important concept in fluids dynamics and aerodynamic analysis. So we're going to spend about half an hour, the first half of the lecture, just looking at some of the theory behind boundary layers, why we look at it, how to calculate it, how to compare theoretical and measured values. And then in the second half, we're going to look at the actual experiment, how you're going to gather your data, how you're going to record it, and how you're going to write it up. Okay? Before we start, just a couple of notes. I've updated the Excel spreadsheet slightly, and I did that on Friday. So if you had downloaded the Excel spreadsheet for the boundary layer experiment before Friday, please delete it. Use the version that's on Blackboard now. Okay? It's version 3 is the one on Blackboard now. It's made it slightly easier to report the data in terms of comparing laminar and turbulent flows, and we'll look at why we do that later on. It's also slightly clearer in the layout as well. The color schemes make it easier to follow the measured and the theoretical values. So please use version 3. Also, there is another health and safety quiz for this experiment. It's very, very similar, okay, because you're in the same lab, but it's separate, so you must do the health and safety quiz for boundary layer experiment as well. Do that before you do the lab. I suggest doing it today. Okay, so let's have a little discussion about wind tunnels. So when we're doing wind tunnel experiments, why are we doing wind tunnel experiments? What really are the 2 main things we're looking at when we test something in a wind tunnel? There's lots of things we're experimenting, but what really are the 2 most obvious things we're looking to measure in a wind tunnel? Anyone? Okay, so wind speed is obviously one of the parameters that we control quite tightly. Lift and drag, yeah. So most of the time when we're doing basic wind tunnel experiments, we're looking to measure lift and drag. Now you've done an experiment where you've looked at both of those. The boundary layer is more concerned with the drag, okay? And why do we look at drag, okay? What actually causes drag? Do we know? Say again? Resistance, okay. So when you're trying to move something through air, yes, you get a resistance. Why do you get a resistance? Say that again? Not streamlined. Well, not quite. Okay, so when we're trying to move through air or through whatever fluid, okay, it's difficult to move that fluid out the way, and the more, well, I'm looking for a term here, the more something a fluid is, the more difficult it is to move through it. Viscosity, yes, viscosity and density. Okay, so when we're trying to move through a fluid, viscosity is what causes it all to sort of hold together, stick together, and that's what makes it difficult to move through. And viscosity is what causes drag. So due to viscosity, which we can think of as the stickiness of a fluid, and if you're thinking that's not a very technical term for third-year engineering, okay, stickiness, that comes from a description on NASA's website, all right? So if it's good enough for NASA, it's good enough for me, okay? So stickiness, what makes all the fluid particles stick together, and that's what makes it difficult to move through a fluid. When a fluid moves through, that viscosity, that stickiness, will cause those particles to stick to the object that's trying to move through that fluid. When that happens, that layer of particles, that first layer of particles sticks to the surface. The velocity is 0. So the particles, if we think of it in a series of layers or streamlines, that layer, one layer above, gets slowed down, and so on as we go up, until eventually you get a layer of particles that moves at the same speed as the free stream. And that, all those layers of slower moving particles, is our boundary layer. And that sticking to the surface is what causes the drag force and slows things down. So by studying the boundary layer, we design our car or our wing or our blade or whatever it is we're designing to minimize that drag force. And that's how we design things to have good aerodynamics. So that is why we study the boundary layer. And if we think of it in terms of very simple engineering, okay, so we've got a wind tunnel test section there, and we've got a surface that we're going to measure the boundary layer over. Well, we have a free stream velocity. That's what we control. So we set our wind tunnel to have a certain free stream velocity. So when our fluid particles come in, the very first layer will come in and they will stick to the surface, okay? That layer has 0 velocity. The layer one above that, okay, does manage to keep moving, but it gets slowed down due to that stuck layer of particles. So it moves with some velocity u that is slower than the free stream velocity u0. The layer above that moves slightly faster, and so on, until eventually one layer there moves with the same velocity as the free stream. Okay, so the velocity of that layer u is the same as the free stream velocity u0, so the velocity ratio, one over the other, equals 1, and that is the edge of our boundary layer. Okay, so everything below that is our boundary layer. And the velocity profile then, if you plot it, it forms this parabolic profile, and that's what forms that common parabolic velocity profile that you get within the boundary layer. Okay, so although we say in theory when u over u0, the velocity profile equals 1, that's the edge of our boundary layer, in practice it's very difficult to actually measure that exactly. So when we're doing this in practice, we tend to take the velocity ratio as 0.99, otherwise it's very, very difficult to measure that exact point where the boundary layer meets the free stream velocity. In some cases as well, you can actually end up with a boundary layer that goes with a velocity ratio slightly above 1. That's slightly difficult to understand. How can you have a boundary layer that's moving faster than the free stream? Won't probably happen to a great extent, but it's to do with pressure differences and air speeding up due to the reduced pressure. But Nick will go into that, I think, in some detail in next week's lecture. So as far as we're concerned, when we're looking for the edge of the boundary layer, we take it when the velocity ratio is 0.99. And a typical laminar boundary layer growth looks something like this, okay? So where you have your flat plate, the first point on the surface there, the boundary layer begins to grow from that point, and the thickness increases with this kind of profile the further you go down the plate. So as distance x increases, the boundary layer grows, and you have this velocity profile within that boundary layer. Okay, so this describes the laminar boundary layer growth. We can have turbulent boundary layers as well, and at some point it will transition from laminar to turbulent, and we're going to have a look at that in a little while, because that's what we will be looking for in the experiment. Okay, so important concept again in this lab. You looked at it 2 weeks ago, Reynolds number. Okay, so this is coming back again. The Reynolds number, it's a dimensionless number that expresses whether the viscous or inertial forces dominate for a particular flow. Okay, so the Reynolds number, it's a ratio of the viscous forces, that's the bottom term, to the inertial forces, that's the top term. And this is important because it tells us whether the flow is laminar or turbulent. Okay, so that's our Reynolds number. We have the inertial forces on the top, the viscous forces on the bottom. Inertial forces means the tendency to move around. Viscous forces means the tendency to stick together. So obviously, if the viscous forces are dominant, everything wants to stay in place, wants to move smoothly in a laminar flow. So if you have dominant viscous forces, that means you've got a laminar flow. Dominant inertial forces, that means everything's got a lot of energy, it wants to move around, that's what causes turbulence. So if your inertial forces are dominant, that gives you a turbulent flow. And we can put this in terms of numbers, thanks to Osborne-Reynolds experiments that he did back in 1883. Okay, so based on those experiments, we generally use these numbers. If you have a Reynolds number lower than 2,300, that indicates laminar flow. And if you have a Reynolds number above 4,000, that indicates turbulent flow. And if you're wondering what happens in between, that's transition flow, where you've got a bit of both behaviors going on at the same time. And as I say, we use those values based on Osborne-Reynolds experiments, and lots of empirical evidence since then that shows that that kind of holds true for most experiments that we do. So that's our typical Reynolds number up there. What you're going to see in the experiments that you'll do now is the Reynolds number written this way. It's pretty much the same equation. Okay, don't be put off though. REX just means our Reynolds number at any distance x along the boundary layer plate that we're going to be doing the experiment on. Okay, so L in the top equation just refers to some characteristic length. X, it's the same thing, it's just a distance in the x direction, but we refer to that as the local Reynolds number because we're going to calculate the Reynolds number at several different points along the plate. And because the Reynolds number is a function of distance x, that number will increase as you go down the plate. Okay, so is the free stream in the wind tunnel laminar or turbulent? Shout out. Turbulent, yes. How do you know it's turbulent? Say again? Yes, it's high Reynolds number, okay? Some of you may just say, we know it's turbulent because Nick told us 2 weeks ago, okay? Yes, he did tell you that. This wind tunnel, it's, the free stream's always going to be turbulent. We know that because if we actually calculate the Reynolds number, then we can see that, okay? So in the experiment you're going to do, the boundary layer, your minimum airspeed is going to be 20 meters a second. You're going to test again at 25 and 30. So we know the density of air, we know the viscosity of air. So therefore, if we put that into our Reynolds number equation, we can see that it only takes 3 millimeters down that test section before the Reynolds number turns turbulent, okay? So after just 3 millimeters, Reynolds number is already 4,033, okay? So that flow is turbulent after a very, very short distance. On the previous slide, I showed you those values. So Reynolds number greater than 4,000 indicates turbulent flow. Your first measurement point, by the way, is going to be at 40 millimeters, so because, as I say, Reynolds number is a function of distance, it'll be greatly increased beyond the turbulent limit there. So in all cases, the free stream, the main body of air moving through your wind tunnel experiment, is turbulent, and that's why. So in order to measure the boundary layer formed in the experiment, we're going to have to measure the velocity. So how do you measure velocity in a wind tunnel experiment or in any moving air experiment? How do we actually physically measure the velocity of air?
The speed of the fan?
Not quite, because how do you know that the fan is actually producing the velocity, the flow through the section that you want? Yes? Yes, a pitot tube. And what does a pitot tube actually measure? Pressure, yeah, okay. So we measure pressure, and then we use Bernoulli's equation to find the velocity. Okay, so this is a simplified version of Bernoulli's equation, but this is all we need to find the velocity. So we have our ambient pressure, we have our pressure at our pitot tube, and we have the density, and that's all we need to calculate the velocity. So that's what you're going to measure. You're going to measure pressure at lots of different tapping points within the boundary layer section, and you're going to use that to find the velocity, and you're going to use the velocity then to calculate the velocity ratio and work out where the edge of the boundary layer is. The experimental equipment looks something like this, okay? So you'll have this flat plate, and it's fitted with these 5 little foils, okay, and they're attached vertically to the surface of the boundary layer plate, and they are fixed at these distances in the x direction along the plate. And within each one of those foils, there are 5 tiny pitot holes drilled into the leading edge of the foil at various heights here. So each one of those little pitot holes has a tube attached to it, and so you can measure the pressure at each of those 5 points at each of those 5 locations, so 25 pressure channels in total. If we look at that a little bit closer up, okay, so there's just one of your foils, there's the tapping heights. Now what's going to happen is you will measure the pressure at each of those points, you'll convert that to find the velocity, and if your velocity is lower than the free stream, if it's less than 0.99 of the velocity ratio, you know you are still inside the boundary layer. If your velocity at that tapping point is equal to the free stream, it's outside the boundary layer, okay? Now remember, just because it's equal doesn't mean that is the edge of the boundary layer, because as soon as you get to the edge of the boundary layer, the velocity ratio is 1 all the way up, okay? So you have to then plot that on a curve and look for the point on that curve where it crosses the 0.99 threshold, and that gives you your height, y, of the boundary layer. Okay, so when you plot that, it'll form a curve that looks something like this. Okay, there's your velocity ratio. So the velocity in the boundary layer divided by the free stream velocity, and then I'll form a curve like this where it equals 0.99. That's where you read off the height of your boundary layer. Okay, so that's how you measure it. That's how you're going to calculate it from the measured values. How do we compare that to the theory? I'm not going to go too much into the theory of boundary layer derivations. Okay, you've probably done that at some point in fluid dynamics anyway. Nick's gone over a little bit of the theory behind fluid flows in previous lectures, and we'll look at it again when we get onto the CFD analysis. Okay, but all you need to know really is that we're going to use the Blasius solution to boundary layer flows in order to get our theoretical values. And Blasius, his values came from, well, Prandtl originally used a reduced version of the Navier-Stokes equation to describe boundary layer flows by removing certain terms. Blasius then solved that for a simplified version of flow over a single flat plate. Okay, so that's what Blasius's solution is all about. It's just flow over a single flat plate. From his work, we arrive at these two equations, which are going to be important to you, that describe the boundary layer thickness in terms of the Reynolds number and the distance x along the plate. Okay, so there are two equations, both to find boundary layer thickness. One if you've got a laminar boundary layer, the other if you've got a turbulent boundary layer. Okay? A couple of slides ago, I showed you typical boundary layer growth for a laminar flow. What happens when that turns turbulent is something like this. Okay? So before I just showed you the laminar region here, that's what the boundary layer growth typically looks like. The further you go down the plate, the Reynolds number will increase to the extent that the boundary layer turns from laminar flow into turbulent flow as well. Now, right at the start, we discussed why the wind tunnel is turbulent. Now, all of the free stream is turbulent, okay? But it is possible to have a laminar boundary layer within a turbulent free stream, okay? So the boundary layer, whatever's going on up here, will always start off laminar. It will then transition at some point into fully turbulent boundary layer itself. Okay, and based on lots of experimental analysis, okay, we tend to take the value, the Reynolds number, at the transition point. So we tend to take the point at which the boundary layer transitions from laminar to turbulent as a Reynolds number somewhere in the region of 100,000 to 500,000. It's actually, in practice, incredibly difficult, and in theory, it's almost impossible, so you have to rely on experimental measurements. It's still incredibly difficult to pinpoint where that transition actually occurs. So you might think that's quite a large range of values. Yes, it is. Okay, somewhere between the Reynolds number of 100,000 and 500,000, we're going to get transition. It's difficult to pinpoint where exactly in that range it's going to happen. Purely theoretical approaches tend to take a value of 5,000, so they err on the larger side and assume that transition occurs at a Reynolds number of around 500,000. When we come to look at comparing it with the experimental data that you'll measure, you might find it's somewhere in between 100,000 and 500,000. So if you're getting confused and you're thinking, hang on, 10 minutes ago you said you get a turbulent flow when it's over 4,000, and now you're saying it's a turbulent flow when it's over 500,000, different types of flow, okay? So a Reynolds number greater than 4,000 produces turbulent flow in a pipe or in a free stream. A Reynolds number of over 500,000 indicates turbulence just inside the boundary layer, okay? So there's two different types of behavior going on there. You can have a turbulent free stream and a laminar boundary layer, okay? And eventually, at some point, the boundary layer will turn turbulent as well. Here's a quote from a very recent paper, just written last year. Okay, it says, "Today we cannot honestly say that we are capable to accurately predict the transition location subject to free stream turbulence in even the simplest boundary layer flow, namely one developing over a flat plate under zero pressure gradient." Okay, that's the experiment you're doing, flow over a flat plate. And today, in 2017, we still can't accurately predict where that transition occurs. Okay, so it sounds a bit vague. It is. Okay, it's not easy to do. Depends on all kinds of things like surface roughness, the effect of turbulence in the free stream, and so on. The angle, if you're not perfectly at 0 degrees on your flat plate, that's going to have an effect as well. All kinds of things lead to variations in that value. Okay. So let's talk about the experiment and the assignment that you're going to write based on it. So experiment number 2, that's the one you're going to do within the next 2 weeks, ties into assignment 2. Assignment 2 is a combination of 2 different experiments. It's the boundary layer and the stress concentrations. Okay? Talk more about that in a moment. Experiment 2, the objectives are to determine the boundary layer development on a flat plate and compare that with the theoretical calculations. Okay, so that's the important thing. The 2 main points there. Measure the boundary layer. What does it look like? How does that compare with the theory? What you'll have the same wind tunnel that you've just used for the aerofoil experiment. This time it's fitted with the flat plate boundary layer experiment, AF106. The user manual for that is on Blackboard as well, so you can have a read through that. All the equations that I'm putting up on my slides here are coming out of that document as well, so it's all written there, the process we use to calculate the velocity, Reynolds number, and so on. What you need to do in your assignment is then describe how that works, include a picture schematic of the rig, so while you're in the experiment, take photos, draw sketches, remember the layout of what you're actually working with. It is also in the user manual as well. Describe the experimental methodology in your own words. As I say, the manuals are there for explaining how the rig works, but please use your own sketches and photos for the description. Okay, don't just pull the images out of the user manuals, please. As I say, it's the same wind tunnel you've used already, so it has a working section of 305 by 305 millimeters square, and it's 600 millimeters long. The air velocity can go from 0 to 36. You'll be testing at 3 different wind speeds, okay, 20, 25, and 30 meters a second. Noise levels at your ear level are up to 80 decibels, so ear defenders are obviously required again. The experiment itself uses the flat boundary layer plate, which will already be set up inside the wind tunnel. You don't need to adjust anything this time. It's set at 0 degrees, so there's nothing to actually change on the wind tunnel itself. And the data is again collected via the same system, just set up slightly differently for the boundary layer experiment. So a few important things to note. As I say, you must have completed the Blackboard health and safety test. Please listen carefully to the instructions given by the demonstrators at the start of the lab, okay? They'll give you a brief sort of 5-minute introduction. I'll be there as well. Do not attempt to adjust any of the fixtures or components on the boundary layer plates, please. It's set up at 0 degrees. There's no need to change anything at all on the experiment this time, and that does mean the experiment is actually quite quick to run. As last time, you've got an hour and a quarter to complete it. If you really know what you're doing, you can probably do all of this in about 20 minutes, okay? But I would like you to then repeat readings as well if you've got the time, and then that'll take you a little bit longer. While you're there, you will need to record the local ambient pressure, okay? There's a little monitor on the desk, gives you the same readings as last time, okay? So convert the ambient pressure from hectopascals to pascals and the ambient temperature from degrees C to Kelvin. You will also need to make a note of which 2 of the pitot tube channels are recording the upstream and downstream wall tappings, okay? So you've got, as I say, 25 different channels which are measuring the 5 different heights on the 5 different foils. That gives you 25 pressure channels. There will be a further 2 pressure channels plugged in which are measuring the upstream and downstream free stream pressure. Okay? Now, at a single velocity, those 2 values should read the same. Okay? And all you will need to do is just take the average of those 2 readings. As I say, they should be the same, and it just gives you 1 value. Just make sure you know on the table of data which 2 channels those are. The way it's been set up in the past is that channels 1 to 25 will all be for the boundary layer plate foils. There will then be a blank channel, 26 will all have 0 readings, and then channels 27 and 28 should be the 2 wall tappings, okay? But the technician is setting it up right now. He'll be able to tell you in the lab which 2 those are as well. So data acquisition system works very similar to the to the aerofoil experiment, I believe, as well. You were taking readings taking 10 readings 2 seconds apart. So as soon as you click go on the software, it takes a series of 10 readings 2 seconds apart. So obviously then you need to average those later. What I'd like you to do if you've got time is to repeat each wind speed 2 or 3 times. Okay, that gives you just a greater set of data to try and get a better average out. So you will have to average all of those readings that you get into a single value of PT per pitot tube per wind speed. Okay, don't average across all 3 different wind speeds, just average for each wind speed. What I recommend is you do that in a separate Excel document. So I'm going to give you an Excel spreadsheet, which I say you download from Blackboard, and that's going to do a lot of the work for you. But when you get this raw data, just open it up. You should be able to just drag and drop the HTML files into a blank Excel spreadsheet, manipulate the data however you want. Okay, while you're doing this in that spreadsheet that you're going to do yourself, you might as well calculate the standard deviation so you can get some idea of the error, the deviation from the average reading in each of those pitot tubes. And that will be useful later when you compare the error in your measured data against the theoretical data. Okay, the Excel function for doing standard deviation is there on the board, just equals STDEV, and then your range of values. Not really much effort required there. The raw data you get will look something like this. Okay, so let's assume that's all the same wind speeds. Let's assume those are three repeats for 20 meters a second. Okay, so you'll have your 25 pitot tube channels for the boundary layer plate, a column of zeros, and then channels 27 and 28 there were set up for the upstream and downstream wall pressures. And if you've repeated the same wind speed 3 times, just do a total average for all of those. So you'll end up with just one row or one column of 25 values of PT, your averaged upstream and downstream values, and your averaged wind speed. What you're going to do with that, it'll be obvious when you see the Excel spreadsheet that you download from Blackboard, which looks something like this. Okay, it's set up to do a lot of the work for you. Okay, so all you have to do is go to the tabs that say data collection for 20 meters a second, 25 and 30, and just feed in your averaged values into that column there, as well as including the static wall pressures, the ambient temperature and pressure and so on. Just feed in your average values for the wind speed into that column. It'll do everything else on this tab for you. Okay, so what it's doing, it's giving you the Reynolds number, it's giving you the theoretical laminar boundary layer thickness, the theoretical turbulent boundary layer thickness, and it's plotting the velocity profile at each of those 5 foils on the boundary layer plate, so you can read off the point where it crosses 0.99 and work out your measured boundary layer height. Okay, 3 tabs, 1 for each wind speed there. Okay, so those 5 graphs that it plots one of those velocity profiles for each of the little foils on the boundary layer plate. So at each foil, you can calculate, or rather just read off from the graph, the point at which it crosses 0.99, and that is your boundary layer thickness. Alternatively, at the bottom of the spreadsheet, okay, so here, this little table is doing that calculation automatically. So I'm perfectly happy for you to just read off the graph if that's what you want to do. Alternatively, this little table at the bottom is doing it for you. So it's using some kind of interpolation there. So it's interpolating off the graph in between those 2 data points, the one that's beyond 0.99 and the one that's in front of 0.99, to work out where approximately that 0.9 crossing point is. What might happen sometimes if your velocity profile doesn't actually reach 0.99, it will return ref, and so there's a separate forecasting function that works out what it should be if that same function were to carry on. Now, you don't have to know what is going on here, okay? As I say, I'm perfectly happy for you to either read the value off the graph or just use the value that's given to you from these tables. It's fine, okay? I'm just showing you what that is in case you see it in the spreadsheet and haven't got a clue what's going on. So what that'll do is you'll have then another tab towards the front, which is called Data Summary. And this brings all of that data together. Okay, so all of those 3 wind speeds, it'll give you your column of your measured boundary layer thickness, and it'll give you the values of the boundary layer thickness from the theory, both for laminar and turbulent flows. Okay, now what you have to do at this point is then decide which theoretical value you're going to use, because it'll automatically plot the measured ones for you. You then have to decide, because obviously I want a comparison graph, whether it's the laminar or the turbulent boundary layer thickness that you want to plot. Now let me just show you this on the Excel spreadsheet using some example data, so hopefully you can get an idea of what's going on. Okay, so here's a version of that spreadsheet with some data I've actually got. As I say, all I've done is fed in the values from the experiment. It's automatically plotted the measured boundary layer thickness here. What you'll notice straight away is that you've got a bit of an anomalous data point there where the boundary layer thickness is much thicker at the start of the plate. That's probably due to turbulence induced by the first sort of contact point, the leading edge of the plate. It's not ideal, it isn't really what happens in theory, but that's probably what's going on there, and then the boundary layer increases with this kind of profile the further we go down the plate. Now, if I were to just compare that to the theoretical values, now what did we say earlier? We said in the boundary layer, a Reynolds number below about 500,000 is still before the transition point. So if we take a Reynolds number of 500,000 as the transition point, look, our maximum Reynolds number there is 403,000. So in theory, if we use 500,000, all of this should be a laminar boundary layer. So if I simply feed in the laminar values, okay, so that's the theoretical boundary layer profile that I should have. And as you can see, it doesn't really match the measured data very well there. If I were to use the turbulent values instead, okay, it's a little bit closer, but still not quite right. Okay, it doesn't quite match the same profile. But there's no real reason for me to use the turbulent conditions, because definitely at the lower Reynolds numbers we'd still be below turbulent behavior. So what's actually happening there is the transition point is somewhere in between. So if I start off with the laminar values, let's see, well, if we say that maybe the transition point is happening somewhere here at a Reynolds number of about 300,000, so if I use for that one the turbulent value instead, there we go. That's starting to look like it matches it a little bit better, doesn't it? So what I've done there is I've used the laminar boundary layer theoretical values at the start, and that's much closer to what actually happens in the experiment. And then at some point between there, at some point around 200,000-300,000 Reynolds number, is going to transition into turbulent behavior. And if I do that, then it matches the measured values much more closely. So that's the idea of the experiment. That's what we're trying to do, match the theoretical boundary layer to the measured values. Okay, now that, I'm not necessarily saying that's the right answer. First of all, your data may not look quite the same as mine. Second of all, maybe you decided that actually that point should have transitioned into turbulent flow as well. Again, if that matches your curve that you've measured much better, then fine. As long as you can justify it in the description, that's what I'm looking for. Because as you can see from the quote, it's very difficult to predict, very difficult to determine how this behavior is going to happen. So that's what I'm looking for you to do. Use your intuition to see whether you have transitioned from laminar to turbulent boundary layers and at what point that has occurred. Okay, so that's what you'll be doing on that tab. Okay, so those two columns there are the laminar and turbulent theoretical values, and it's up to you to decide which ones you're going to feed into that column. Okay, so as I say, think about what the theory says, and then think about what your measured data says as well, and try and come up with some sort of, at some point in between the two. At the bottom of that Excel spreadsheet, there's a blank graph where you can combine all of these 6 lines onto one graph. So you'll be comparing the 3 measured wind speeds against the 3 theoretical wind speeds. Obviously, I want you to do a little bit of work there. Just combine them all onto one graph. That will make it easier to put into your report because you've only got limited space. Please come up with an appropriate color scheme or pattern scheme so that it's obvious which ones you're comparing. And if you think it's appropriate based on your standard deviation, please add error bars to that graph as well so you can see how much error you should be getting in your measured results. Adding error bars, just go to Chart Tools, add Chart Element, error bars. You should be able to work out what you're doing from there on. Okay, so a little bit about the report. The results and discussion required. Use the Excel template provided for all calculations. You're very lucky, it does a lot of the work for you. Okay, there's no real need to go into actually doing any of the calculations. A lot of that is done for you. As I say, come up with your average values and your standard deviation for each tap point. When you come to writing your report, I want you to include some comparison of the normalized velocity profiles at different tap points. Let me go back a few slides. Okay, those are your normalized velocity profiles. So I want you to compare at least 2 or 3 of those. Which ones you compare, it's up to you. You compare the same wind speed at different points down the plate. You can compare different wind speeds at the same point. It's up to you. I just want you to show that you've thought about how the velocity profile differs at different X points or at different wind speeds. Okay? You've got limited space, so I would suggest you may want to combine several onto one graph, as long as it doesn't look too cluttered. So as I say, how many graphs, velocities, and tap points you display is up to you. Utilize the limited space to maximum effect and include a short sentence describing what you've plotted there. Make sure graphs are clear, number and caption the graphs, increase font size from the Excel spreadsheet if necessary as well. I want you to talk about at what value of the normalized velocity is the full free stream velocity assumed to be reached. What is that value? 0.99. Okay, we've just been talking about it in the lab. That's all you have to say. Okay, it's all you have to say. Just think about, in the most simplest terms, what these instructions are telling you. So the normalized velocity, we assume it reaches the free stream velocity at 0.99. Just write that in somewhere. How does this relate to boundary layer thickness? Yeah, that is the boundary layer thickness. Okay, so at 0.99, that is the boundary layer thickness. That's how it relates. Okay, second bullet point, include a table summarizing for each velocity and at each foil the measured and theoretical boundary layer thickness. Okay, so that slide on Excel I showed you just a few moments ago. Okay, you've got a column comparing theoretical and measured. I just want you to join those together so you've got each different wind speed. Based on those measurements, can you state at what distance you would expect the laminar to turbulent transition to occur along the plate? That's what I've just done there, okay, trying to get my theoretical and measured curves to match. Based on that, you can kind of infer at what points you are expecting the transition to occur. Okay, what are the Reynolds numbers at the first foil for each velocity? Just a sentence. Okay, on a single graph, plot the measured boundary layer thickness for all 3 velocities against the theoretical boundary layer thickness. So that's the blank graph at the bottom of the data summary tab. Okay, just populate that with your 3 different lines, measured and theoretical, 6 lines in total, and include that in your report. As I say, add error bars if you think that's necessary, showing the level of deviation in the experimental data. And of course, a little bit of discussion about what that graph is and what it shows. Second to last bullet point, describe the boundary layer growth observed in the experiment. So describe how the growth is, where it transitions, and so on. How does the empirical or theoretical boundary layer growth compare with the experiment? Do they match up quite well? Are they quite widely different? And if so, why is that? Quantify the maximum differences, so in terms of a number or a percent, how much are they different? And comment on any points, like I did there, where one of the data points is clearly anomalous or way outside the expected value, and see if you can come up with a reason why that is. Are the theory to experimental differences higher or lower than expected? If they're higher or lower, what are the reasons? And final bullet point, how does the boundary layer thickness change with increasing flow velocity? Does it increase? Does it decrease? Does it stay the same? So for a lot of these, okay, they are fairly simple and require not too much discussion to answer, but just make sure you answer all of those bullet points in the results and discussion required. You obviously have fairly limited space to display all of this information, okay? So as I say, report C2 combines the boundary layer and the stress concentration experiments into a single report. You've only got 4 pages to write all of this, okay? So use short, concise statements. Don't write too much if you don't have to, and choose carefully which graphs, tables, and values you want or need to show. Don't go off and show too many graphs if you don't have to, and don't make them too cluttered or difficult to read. So assignment C2, as I say, it includes the write-up of both experiments. That should read experiment 2 and experiment 3. Okay, so assignment C2 contains experiment 2, which is the boundary layer, and experiment 3, which you'll do in 2 weeks' time, stress concentrations. The deadline for that is 5 p.m. on the 23rd of March. That's for everyone. Okay, and this assignment makes up 30% of the module mark. So your assignment you've just submitted for the first 2 weeks is 20%, this one is 30%, and your final report is worth 50%. Okay? The layout looks something like this. So it's no more than 10 pages in total for both experiments. You've got one cover sheet for the whole report, so that's 1 page. For each experiment, half a page of summary, 1 page on the experimental setup, images, figures, and so on. 2 pages on your results and discussion, including all of your graphs and tables, and half a page on conclusions. And then for the whole report, half a page on a personal reflection and half a page on any references, okay? A minimum of 4, so that's a minimum of 2 for each, but probably a few more than that, yes.
Are we doing it so we're splitting up into 2 separate ones, or do a summary for both of them?
It's completely split up, okay? The way these 2 experiments work, we've put these all into one report to reduce the workload on you, okay? We don't want you to do a separate report for each experiment because that increases your workload. But in reality, these 2 experiments are completely different things, okay? You're doing one that investigates fluid flow, one that investigates mechanical stress concentrations. There's no correlation of any of the data between the 2. It just makes it easier to combine it into one report, so there's less work for you.